Okay, so sorry about that. We're going to be recording this session. If anybody has any objections with the recording, please say so now. Okay, so we began talking about resistors, and resistors are going to be these components that are going to be found in electrical circuits that, according to Ohm's law, which is the basis of all this, is going to give us a relationship between voltage and current. And so the resistive components are going to somehow oppose the flow of current. And these are called resistors. And we already saw the symbol of the resistor is this one that we see here in these diagrams. And so similar to when we were talking about capacitors, we know that resistors in a circuit can be connected in various ways. And remember that there's two basic ways in which we can connect two or more components. One is a series connection. Remember, series connection is like a chain. One's holding hands with the other, that's holding hands with the other, and there's 2 points that connect globally. So this is a this is a series connection. Okay, and again, the series connection is kind of like the chain. Okay. The other type of connection that we have is a parallel connection, and the parallel connection is going to be a connection in which the two terminals of the component, or of all the components, are connected to each other. Okay, so it's like two people holding hands like this. So this is a parallel connection. Now, depending on if we connect the components in series or in parallel, we are going to have, or there is a concept of an equivalent resistance, similar to the concept of an equivalent capacitor. So what does this mean? If we have many resistors connected in an array, we can calculate equivalent resistances, which is sort of a reduction of the circuit, to be able to do the analysis of the components of the circuit. And the equivalent resistance will be one resistance value that has the same effect as having all of the resistances connected together in the array. And so that's called equivalent resistance. Now, things that are important with resistors in series and in parallel, and these are things, by the way, that we already mentioned in capacitance, that apply for series or parallel connections, regardless of if we have a resistor or capacitor. There are certain basic things that apply. And so for a series connection, the current going through the circuit, I'm going to draw the current in blue. The current going through the resistive elements is going to be the same. Whenever we have elements or resistors connected in series, the current is going to be the same current. Okay, it's going to be the same current. Now, remember that when we were talking about capacitors, we weren't talking about current. We were talking about charge. Okay, and if you remember, if we were talking about a connection in series of capacitors, the charge also behaved similarly. So in a series connection, the current is going to be the same throughout all the elements. And remember this, remember the elements, like, think of this as a tube. Think of this as a tube or a pipeline where water is flowing. And so if you've got a tube that has 1, 2, 3, 4 constrictions, the resistance is the constriction, but the flow is going to be the same. The same amount of water that's coming in is going to be coming out. So that's why the current is going to be the same. Now, the voltage is going to be different. Okay, and I'm going to draw the voltage in orange. So because we have a relationship due to Ohm's law that says that voltage equals current times resistance, if the current is the same, the voltage drops are going to be different in each element. And so here we're going to have a V1, here we're going to have a V2, here we're going to have a V3, and here we're going to have a V4. Okay, so in series, current is the same, voltages are different. And all of this comes because we've got one total voltage here in the circuit. Okay. And the sum of these voltages has to be equal to the total voltage of the circuit that we've got there. Okay. Questions up to this point. By the way, and going back to JC made that question last session, because in capacitors, in one configuration we added them, and the other the equivalent capacitance was the reciprocal of the sum of the reciprocals. And if that same thing applies here with the resistance, actually no, it's the other way around, but we haven't gotten to that yet. Okay, so these are the characteristics of voltage and current in series circuit. Okay. Now, for a parallel circuit, there is going to be one voltage. There's going to be one main voltage, V. And this voltage V, because of the parallel connection, is going to be exactly the same one in each element. So this resistor has a V, this resistor has a V, this resistor has a V, and this resistor has a V. All the resistors are going to have the same voltage. What's going to change here, or what's going to be different?
The current.
The current, correct, JC, it's going to be the current. So what's happening here is, and again, think about the analogy of the, of the fluids, but there's going to be one major current that's going to be going through the circuit. We're going to call this I. And that current, when it gets to this point, is going to be divided, in this case, into 4. So we're going to have one current here going through this resistor. It's going to be I1. There's going to be another current going through the resistor. That's going to be I2. There's going to be another current going through this resistor. That's going to be I3. And lastly, there's going to be another current going through this resistor that's going to be called I4. Okay. And the sum of those is going to be equal to the total current in the circuit, which is equal to I. Okay. And so those are the rules. Current in series is the same, voltage is different. Voltage in parallel is the same, current is different. Okay? Questions up to this point before we jump on to the next part that has to do with the equivalent resistances. Okay. Okay. Good. Okay. Now, let's talk about equivalent resistances. I'm going to clear this and we're going to jump to the next slide. If anybody has any question, please stop me. Let's talk about resistors in series. Now, this is very important because it can get confusing. Resistances are governed by Ohm's law, which is V equals, and this is just math, okay? Resistances are governed by Ohm's law that says that voltage equals resistance times current. Okay, let's see, because this is going to be in the exam. What is the relationship, the mathematical formula for the capacitances and voltages? It's also a formula with three elements. How is that formula represented? What's the formula that relates capacitance, voltage, and charge? How is that formula?
Professor, are you talking about the triangle?
No, that's the Ohm's law. This is the one that
It was something of, wasn't it like c squared over 2, something like that? Let me check.
Yeah, let's do this. Remember that you guys have your notes. I'm not asking you, this isn't a job interview. I'm not asking you to look for it by heart. You've got your notes. This is Ohm's law. Remember this triangle, Lucia, this is Ohm's law that defines this. But what formula are we?
It's the one of the U. The
No,
U equals, no.
that's
Okay.
energy. That's
Okay.
energy. Okay. What formula
Isn't it
relates?
Q equals CV?
Correct. Got it. Perfect. Q equals CV. Charge equals capacitance times voltage. And if we present this is going to be V equals Q divided by C. Notice that here, this is just math, okay? This is just, so we know where this is coming from. This is a multiplication. Voltage equals the parameter, which is resistance, multiplied by the current. Over here, voltage is equal to the parameter is in the denominator, and the charge is divided by that parameter. So mathematically, these expressions are different. And so when we were talking about capacitors, capacitors in series and in parallel behaved a certain way. Resistors are the opposite, okay? So as to not get confused, or rather understand why you might get confused. In the case of resistors in series, if we have resistors in series, the total resistance or the equivalent resistance is going to be the sum of each of the resistances, okay? What happened with capacitors? Capacitors in parallel was the sum. Here it's the other way around. Resistors in series, the equivalent resistance is going to be the sum of the resistances, okay? And we already mentioned that the same current is going to flow, and the voltage is going to be divided, okay? So equivalent resistance for resistors in series, we're going to add up the resistances, okay? Okay. Now let's look at a problem. Problem number 1, a 9-volt battery is connected to a circuit with 5 resistors in series. 4 of the resistors are 20 ohms and 1 is 10 ohms. And they're asking us to do a few things here. First off, to draw the circuit. I remember we were doing some exercises and somebody, or I was explaining something, we're doing some exercises and somebody said, do we need to draw the circuit? Not always. In some of these exercises, it is important to draw the circuit to visualize how it's configured. Find the equivalent resistance, find the current, find the voltage drop in each resistor, and find the power dissipated by each resistor, okay? This is important. The battery, just so we can relate it, remember that the battery is the EMF, or the element that has the electromotive force. Oh man, I got the hiccups. I got the hiccups. I think it's the air that's in. And so since the battery is the EMF, there's a note here that's important that says that we should assume that the battery, the internal resistance of the battery, we don't care about that, okay? Because remember that the battery internally could have a resistance, and that would mean that instead of being 5 resistors, there would be another resistor that we would have to add. But right now we don't need to consider that, okay? Now, I'm going to give you guys individually, I'm going to give you guys 5 minutes to try to approach this problem. And we're going to solve it here. By the way, you guys, remember, we're going to have an exam coming up. And by the way, the last topic of the exam is going to be this one, we may address a new topic either Friday or Monday, but that is not going to be included. So this is going to be the topic up to which exam number 2 is going to cover. So exam number 2 is going to cover unit 2 and up to this point. Okay. So it's important for you guys to start doing some exercises. Okay. I'm going to solve them here and they're being recorded, but it's important for you guys to practice. So I'm going to give you guys 5 minutes to try to work this out, and then we're going to compare notes and solve it here. So you guys have got 5 minutes starting now. Okay, so let's start solving this. Again, apologies for the hiccups. So would somebody like to give a try as to drawing the circuit? Any volunteers?
I can try, but
Go
I
ahead.
don't know if it's correct.
Don't worry, Lucia. The important thing is to try. If it's not correct, we'll correct anything. But it's good that you would like to try. Give it a try. Just give us a draw of the circuit. It doesn't have to hiccups. I'm sorry. You guys are gonna think I'm drunk. I'm not. It doesn't have to be a perfect or pretty drawing, Lucia. You probably draw better than that. So I'm sorry. Go ahead.
Okay, so I related to the one that you drew, like the other side. So I don't. It's because I don't want to look dumb doing this.
You do not, Lucia. The last thing you're going to look at. It's serious. I'm glad that students raise their hands and want to participate. It's important. Okay. So no, do not worry about that. And I would be a terrible teacher if I made you feel that way. And so,
No.
okay.
So, and then like it's 1, 2, 3, and 4 because
Mhm.
it says that there are 4 series. I think it's like that.
It says, let me go back a
There's
slide.
5 resistors.
Yeah.
No,
So
no.
we're missing one.
I'm missing one. I'm missing one. Yeah,
Mhm.
I thought there were 4. Okay, there.
Okay. Good. And one thing, Lucia. Okay. Just one thing, because we're to try to have the drawings of the circuits complete. Okay, so you drew the 5 resistors. Perfect. We need to identify them. Okay. So either let's call them R1, R2, R3, R4, and R5. Okay. Let's identify them, because the other way we just have 5 resistors there. We don't have any idea what they are. So let's put a name to each of them. We call them R1, R2, R3, R4, and R5. Just
Okay, let me do that.
and I'm gonna help you out here with some notes while we do this. R1 is going to be the same as R2. It's going to be the same as R3. And I believe that the problem states that these are 20 ohms. Okay, Lucia, are you going to, can you put there we go. Oh, that's much nicer than my drawings. That's but it's 1, 2, 3, and 4. And let's not put the dot there. The just R1.
Oh yes, it's because I put space. That's why the one came out, like the dot came out. I know it doesn't have a dot. Like I was doing the space when I was typing it, and I forgot like to take away the dot. Should I do it again?
No, that's fine. That's fine.
Okay.
Thank you very much, Lucia. And just help me out so I don't have to go back to the previous slide. So the problem says that R1, R2, and R3 are 20 ohms, I believe, and the other 2 are 10 ohms, right?
Yes, I think so.
Okay.
It's because I put 4 equals 20 ohms and 1 equals 10, but maybe
Oh, actually, it doesn't matter. For the purpose of the calculation, it doesn't.
Okay.
Professor,
Yes,
I have a question.
go ahead.
The circuit can be also like a square.
Yeah, we're not, that's a good observation, Carmina. We're not done. Okay, we're not done with the drawing. So thank you very much, Lucia, and for this. Now, we're not, this isn't a complete or accurate, this isn't a complete, I'm sorry, drawing of the circuit. Why? The problem says that there are 5 resistors. Lucia correctly drew 5 resistors and identified them. What does the problem also say that the circuit has?
The battery.
A battery.
We've got a 9-volt battery, okay? Batteries have different symbologies, by the way. Batteries have different symbols, okay? Right now, for this course, I'm not gonna focus that much on symbology. Right now, we're just gonna draw batteries as circles or sources, power sources, or EMFs as circles. And we're gonna indicate a polarity. Okay, because right now we're talking about DC circuits. So we're going to indicate a polarity, plus, minus. And I'm going to call this VS. The VS means it's the source, okay? And VS, what is the value of the battery source? What voltage do we have there?
9.
9 volts, perfect. Now, actually, Lucia and the rest of you, we haven't defined what a circuit is. We're using the word circuit and we talk about circuits, but we haven't formally defined what a circuit is. What do you think a circuit is, or how could we generally define a circuit? And by the way, think about electronics or think about anything that you call a circuit. How many of you like racing? You know that racing, they call them racing circuits? Okay, what is a circuit then? Anybody give it a try?
Yes,
Omar?
make sure that is closed.
Well, let's go with that, Omar. A circuit is going to be generally defined by a path. By a path that something is going to go along that path. Okay? And so it's a path. Now, there can be an open circuit and a closed circuit. Okay? But a circuit is going to be a path where, in this case, for electrical purposes, a circuit is going to be a path where electricity or electric current can flow. So if we just draw the resistors like that, if nothing's connected to the resistors, there's not going to be a flow. So to complete the circuit, we need to do this. We need to connect the resistors to the battery. Okay? Is that part clear to everybody? So Lucia, you drew the 5 resistors, that's correct. We need to add the power source and we need to connect everything. Okay. By the way, this is one way of representing the circuit, okay? Another way of representing exactly the same circuit, I could have said this. This is exactly the same circuit. Is that clear to everybody? I'm just rearranging it, but it's exactly the same. Okay.
Both of
So
them are circles. I'm sorry, circuits.
yeah, both of them are circuits. Both of them are the same circuit, actually. Just it's a different way of looking at the circuit. Okay. But both of them are exactly the same circuit. It's a power supply with 5 resistors connected in series. Okay. Okay. Questions up to this point? Are we doing good? Now we need to calculate the equivalent resistance. And the equivalent resistance means that this circuit, we want to turn it into, or we want to represent it as an equivalent circuit where we've still got our power source. But instead of having 5 resistors, I want to identify a value of one resistor that has exactly the same effect as the, I'm going to call it RT. No, I don't want to call it RT because it's not the same terminology I'm using. I just don't want to write anymore because my arm is starting to hurt again. Vibranium arm. We want a circuit that is equivalent, or we want a resistor that's equivalent to the other one. And so instead of just having one resistor or 5 resistors, we want one resistance value that's equivalent to all of that, right? How do we calculate that equivalent resistance? Can anybody tell me? According to what we just saw?
It is the addition of every every resistance, a resistor.
Correct, Lucia, because the resistances are connected in series. And we just said that the equivalent resistance for a series array is going to be the sum of each of the resistances, okay? Which in this case would be R1 plus R2 plus R3, whoops, plus R4 plus R5, okay? And in this case, what is this equivalent to if we do the calculation? What's the equivalent resistance then for this circuit?
90.
90, which would be, let's see, 20 plus 20, it's 40, plus 20 is 60, plus 10 is 70, plus 10 is 80. Okay.
Professor, is
Professor,
because the first 4 are
yeah.
20. And
Oh,
then
just
Yes.
one.
is 10.
Oh, okay. Oh, thank you. We're going to do a break after we finish this. Oh, so let me correct this because I asked at the beginning. So in this case, the first 4 are 20 and just the last one is 10. Okay, that's important. Remember that you guys, we're a team. You guys are helping me out, so I'm expecting that all of you pay attention. So just if I write down a mistake at the beginning, tell me at the beginning, okay?
So I think that when you said it correctly, but
I said it correctly, but I didn't write it correctly, maybe. So again, my just don't tell my wife this but I do make mistakes sometimes. And she constantly reminds me that I do. She's the brains of the family, by the way, not me. So I do make mistakes, even though I don't like to admit it. So yeah. So okay. So so correct. It's what JC said. So it's 20 plus 20 plus 20 plus 20 is 80 plus 10 is 90. It's 90 ohms is the equivalent resistance. I believe according to what we defined in the problem, this is A, which is drawing the circuit, and this is B, which is the equivalent resistance. Okay. Okay. Questions up to this point before we break?
no questions.
No. Okay. Good. We're going to do a break, and we'll be back. Okay. So here we got A and B. A is draw the circuit. B is find the equivalent resistance of the circuit. C is to find the current through each of the resistors. Okay. So if this is a series circuit, then there's going to be one current that is going through the resistors. It's going to be the same current in each of the resistors. How can we find that current? Well, this is the same current that's going to be going through the equivalent resistor. And so this means that I can find the current using Ohm's law. So I know that voltage is equal to current times resistor. And right now we're talking about the the current then from Ohm's law is voltage divided by resistance. And in this case, the voltage and resistance that we're talking about is going to be the source voltage divided by the equivalent resistance. Okay, so the current or the total current for the circuit is going to be equal to the voltage source, which in this case is 9 volts, divided by the equivalent resistance, which we had found is 90 ohms. So 9 divided by 90, this is going to be equal to 0.1. I'm going to write this down with a different color, actually. Just to be congruent and make it a little bit. So the current is going to be equal to, we can even write it down here, 9 volts divided by 90 ohms. Okay, and this means that the current is going to be equal to 0.1. What are going to be the units for the, what are the units for the current?
Amperes.
Amperes, correct. And amperes sounds weird in English. So we usually abbreviate these as amps. So it's 0.1 amps. Okay. Questions with this one? Is this part clear? Carmina, please go ahead.
If it says find the current through each resistor.
Yeah.
Okay.
Yeah. Go ahead. I'm sorry, I interrupted. Go
No,
ahead.
sorry. I was gonna say, this is the final answer, or we have to do separately?
Oh, okay, so that's a very good question. I'm glad you asked that, Carmina. So remember, when we are talking about series resistors, there's a current I, and this is going to be the current in each of the resistors. There's going to be, because they're connected in series, the current is the same in each of the 5 resistors. Okay. So this means that the current in each resistor is going to be 0.1 amps. Okay, because they're in series. It's going to be one current that's going to be going through the whole resistor. Okay, so the whole series of resistors. Okay, and that's because they're connected in series. So if the problem says, give me the current in each resistor, the total current is going to be 0.1, and this is going to be the same as each of the currents in each of the resistors. Okay, is that part clear?
Can you repeat that, Professor?
Yes, thank you.
Okay, so again, because the circuit is a series circuit, the current is going to be the same current in all of the resistors. So I just found the total current, which is I, which is 0.1 amps. This is going to be the same current that we have in each of the resistors. Why? Because they're connected in series.
Yes, perfect. Thank you.
Okay, so 2 equals 3 equals 4 and equals I5. Okay. Let me do a screen save of this. Okay. Questions with this one before we move on? So this is C. What is the next one? What does D say? D says that we should find, if I'm not mistaken, we should find the voltages in each of the resistors. Now, the current is going to be the same, but the voltage is going to be different. The voltages are going to be different, and that's the basic rule here with the circuit. So, okay, give me one moment here. Okay, I'm going to clear this and let's talk about the voltages. Now, what's going to be happening here is that each of the resistors is going to have a voltage, or there's going to be what we call a voltage drop. What does this mean? That we're going to have a voltage V1 here, a voltage, I'm going to write it, oops, I'm going to write it here on top. We're going to have a voltage V1. We're going to have a voltage V2. We're going to have a voltage V3, a voltage V4, and a voltage V5. This again happens because our resistors are in series, okay? Because our resistors are in series. The voltage V1, I'm going to try not to make such a mess here, but the voltage V1 is going to be equal to R1 multiplied by I1. And we already saw that the currents are going to be the same. Voltage V2 is going to be R2 multiplied by I2, and so on and so forth. R3 multiplied by I3, R4 multiplied by I4, and R5 multiplied by I5. Okay. Now, we already established that the currents are the same. I1, I2, I3, and I4 are the same current I that we established, that's it's 0.1 ohms. So in the case of R1, I1, this is going to be equal to R1, 2, 3, and 4. All of them are 20 ohms. Okay. So all of these are going to be equal to 20 ohms. By the way, this is just a specific problem where all of the where there's a bunch of resistances that are the same. We could have them be different. Multiplied by I1, what was the value of the current? Multiplied by the current, what was the value we calculated for the current?
0.1.
0.1. And in the case of this one, we're going to have 10 ohms multiplied by 0.1 amps. Okay, that's too ugly, even for my writing. Okay. And so we can calculate each of these voltages. It's actually very easy. It's actually very easy calculations. We've got then that V1 is equal to 20 times 0.1. This is 2 volts. And this is actually going to be the same as V2. It's also going to be 2 volts. V3 is actually also going to be 2 volts. V4 is going to be 2 volts also. These are actually going to be the same. And V5 is going to be equal to 10 times 0.1. It's going to be 1 volt. Now notice that if we add these 2 plus 2 plus 2 plus 2 plus 1 is going to be equal to, so if we add these, it's going to be equal to the voltage source, which is 9 volts. And that's also important. That has to be congruent, okay? And this is basically what they're asking us to do in D. Okay? Questions with this one before we do the last part, which is the power.
No questions.
Okay. Now for the power of the circuit, let me just say for the power of the circuit, that's relatively easy because the power is going to be, if we remember the expression we had talked about, power is going to be equal to I'm just going to write it here. Power is going to be equal to, there's many ways in which we can do this, but the general representation is that it's going to be voltage times current. So if I want the power in each of the elements, I'm going to have power 1. Each of the elements is going to have its own power. Okay. And something very important, the power supply is also going to have its own power. What's the difference between the power of the power supply and the power of the resistances? Can somebody tell me? Somebody remember? Power, energy. What's the difference between the power that the resistances are going to have and the power that the power source is going to have?
Here, which one is the power source? The circle on the bottom.
Mm-hmm. Remember that there are 2 types of elements that we talked about. 2 types of.
One is passive and the other is active.
Correct. I think it was Karen.
Yes.
Yes, Karen, correct. One is passive and one is active. One is giving or providing power, the others are absorbing it. So the resistors are passive, the power supply is active. So the power that's being consumed by the resistors has to be the power that's being given by the power supply. So we're gonna calculate these quickly here. So this. So power 1, power 2, power 3, power 4, and power 5. Power 1 is going to be voltage 1 multiplied by current 1. Power 2 is going to be voltage 2 multiplied by current 2. Power 3 is voltage 3. Whoops. Multiplied by current 3. Power 4 is voltage 4 multiplied by current 4. And power 5 is voltage 5 multiplied by current 5. And so here for these 4, we already identified that the voltage is going to be the same for these 4 because the resistors are because of the calculations we did previously. And so this is going to be 2 volts multiplied by, what was the current? The current was 0.1 amps. And voltage 5 is going to be, what was voltage 5? Can somebody remember what was voltage 5? 1 volt.
It was 9, no? Oh, no, yes. The resistor, yes. I thought you were saying the power one.
We're going to go to the power source now. But yeah, it's it's 1 volt and it's 1.1 amp. And the power source voltage, the power of the power source is going to be the 9 volts multiplied by, in this case, the total current, which is the voltage of the power source is the voltage source times the total current. And this is going to be 9 volts multiplied by 0.1. Amps. And so these calculations here give us that power 1, or the power for 1 is going to be equal to 2. What are the units? I'm sorry. What are the units for power?
Watts.
Watts. Perfect. Thank you, Lucia. These are going to be watts. And power 3 is also going to be, power 3 is 0.2 watts also. Power 4 is also going to be and power 5 is going to be 0.1 watts. Okay. And the total sum of these is going to be equal to the wattage that we have here in the power source. So 9 times 0.1 is going to be 0.9 watts. And so if we add these, we're going to get the wattage or the total wattage in the power source. Okay, and this is basically what we've got here in E. Okay. Questions with this one?
You said
No.
that at the end you have to add all the watts, or leave them like that.
No, what we're saying is that remember that the power in each resistor, that's the passive. And so 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.1 is 0.9.
Will equal.
That's the, yeah, exactly. That's the energy that's being absorbed. Who's providing the energy? The power source. And what energy is the power source providing? 0.9 watts. So energy isn't, it's only transformed. So the energy of the power source is being given to the resistors. And so the total energy of the resistors has to be equal to the energy that's being given by the power source.
Okay.
Okay.
Thank you.
Okay. Okay.